Okay, this is AP Chemistry's podcast 4.3, and we're going to talk about the trends on the periodic table. So the first trend we're going to talk about is atomic size, and atomic size is the same as atomic radius. It's just the size of the atom. And you can see a picture here that visually shows you what happens with the size of these atoms as we go both down a column and across a row. So hydrogen's pretty small, helium pretty small. But if we get down here where we can see a little better, what you're going to notice is that atomic size gets smaller as you go across the row. And that's because of an increasing nuclear charge. An increasing nuclear charge means you're adding more protons to the nucleus. So within the nucleus, we're adding more and more protons. And we're also adding more electrons into the same energy level. So as we do that, it's creating almost a stronger magnet that pulls these electrons closer to the nucleus and the size decreases. As you go down the row, what you see though is that the size increases, and that's because you're adding energy levels as you move down. So lithium has 2 energy levels, sodium 3, potassium 4. So as you move down, the atomic size gets bigger because you're adding energy levels. As you go across, it's getting smaller because of increasing nuclear charge. Ionization energy is another trend. Ionization energy is the energy that it takes to remove a valence electron. And what you're seeing are different values here. But you'll notice that the general trend from hydrogen to helium, it increases. Lithium is the beginning of a new row. And as we move across this row all the way to the noble gas, you'll see that the general trend is for the ionization energy to increase. Once you hit neon, that's the end of the row, and then you come back to sodium at the start of the next row. And you're going to see again that the general trend is that it increases. So if we wanted to talk about what those general trends were and label them on this periodic table right here, we would say that ionization energy, as you go across the row, it's going to increase. So it increases as you go across the row, and it actually decreases as you go down the row. The reason that it does this, and it's exactly opposite of the size trend, is because the increasing nuclear charge that we talked about that makes the atom smaller also holds those electrons on tighter. And if you think about the number of valence electrons these guys have as we go across the row, lithium would have 1, beryllium would have 2, boron 3, 4, 5, 6, 7, and 8. The more we go across these rows, the less they're going to want to give up their valence electrons. When we get nitrogen, nitrogen wants to pick up 3 more electrons. Oxygen wants to pick up 2 more. Fluorine wants to pick up another. So as we're going from left to right, the elements want to gain electrons, they don't want to lose them. So they're going to hang on to those valence electrons even more tightly. And because their size is smaller, it's easier for them to hang on to them. When you go down the columns, because the atomic size is getting bigger and bigger and bigger with each added energy level, we have what's called the shielding effect. All those inner electrons that are between the nucleus and the valence electrons are shielding the pull of the nucleus on the very outer valence electrons. So it becomes a lot easier to lose electrons. It takes less energy to pull an electron from cesium as compared to sodium, or from iodine as compared to chlorine. So this is opposite of size in terms of the trend that this runs. Okay, there are also first ionization energies, second, thirds, and we can go on and on and on, and that's what these are right here. What you can notice are trends. So the first ionization energy is the energy to remove 1 valence electron. The second ionization energy is the energy required to remove a second electron. So a third would be a third electron. And if you think about this in the table that we're looking at right here, sodium is in column 1A, so it has 1 valence electron. We'll say 1 VE. Magnesium would have 2, aluminum would have 3, and so on down the row here. what you're going to notice is that it's relatively easy. It doesn't take a whole lot of energy to remove the one valence electron from sodium. After that, though, you're going to see this huge jump in the amount of energy that it's going to take to remove another electron. Once that valence electron is gone, this sodium ion is now very stable. It's got a full outer shell. It's holding on to those valence electrons really tightly, so it doesn't want to have another one removed from it. Magnesium, once you've removed its two valence electrons, you see a huge jump because it doesn't want you to take a third one away. We're getting into what they call these core electrons. The core electrons are the electrons that are inside the valence electrons. Aluminum, you can remove 3, but when you want to go to that fourth, you're going to see a really big jump. So there's a good chance when you take the AP chemistry test that you'll see a table like this, and they would ask you if this is element X, Y, and Z, which of these would form a +2 charge. And you would want to pick out element Y because when it makes a big jump from the second to the third, that tells you that it must have had only 2 valence electrons, because when you try to remove a third one, it's just too much energy. It's more stable with the 2 gone, not with the 3. So you can actually get quite a bit of information from looking at a table like this. Why does the energy increase as you increase the number of electrons removed from the atom? We talked about that. At some point you're hitting the core atoms, or the core electrons. Once you've removed the valence electrons, you've hit the core electrons, and then it becomes a lot harder to pull those away because you have a stable atom that you're trying to pull them away from. And then the second question was, why is there such a big jump in energies in certain portions of the table below? And we already talked about that as well. Once you've removed all the valence electrons and you get into the core electrons, you make that big jump. It becomes a lot harder to remove electrons. There's also some other questions that we can ask that relate to ionization energy. It says, why is the ionization energy of oxygen lower than that of nitrogen? What I have here are the 2 orbital box diagrams for oxygen and for nitrogen. And if we look at these, you would think because oxygen is farther to the right of the row, because it goes boron, carbon, nitrogen, oxygen, fluorine, with the general trend, oxygen should have a higher ionization energy than nitrogen, but in fact it doesn't. The reason for this is oxygen only has a full 1s orbital, it has a full 2s orbital, but it does not have a full or a half-filled 2p orbital. So it's actually relatively easy to remove this electron that's right here. If you take that electron away, what you're going to find then is you have a full 1s, a full 2s, and then a half-filled 2p. And we talked about this earlier with orbital box diagrams, that full boxes and half-filled boxes are the most stable. So by losing that one electron, it actually makes oxygen more stable than it was before. This is the most stable. If you look at nitrogens, nitrogen is already like this. It already has a full 1s, a full 2s, and its 2p is half filled. So it takes a little more energy to remove one from nitrogen because it's technically more stable than the oxygen with its extra electron right there. And the same trend you can notice here for aluminum and magnesium. Magnesium has a full 1s, 2s, 2p, and 3s. Aluminum has a full 1s, 2s, 2p, and 3s, but it has this extra electron in the 3p. It's a lot easier, not a lot easier, but the ionization energy is lower for aluminum because it's okay giving up that electron right there, because that makes aluminum more stable. When it ends up with full 1s, 2s, 2p, and 3s, that extra electron gone actually makes it more stable. So aluminum, you're going to see, will have a lower ionization energy because it kind of wants to get rid of that one electron. It'll make it more stable than it would if it had that one there. So you can use the orbital box diagrams to help you figure out why there are some exceptions as you go across the rows. Electron affinity, I believe, is the last periodic trend we're going to talk about. It's a little different than electronegativity because electron affinity is an actual number. It's kilojoules per mole. And what it is, it's the energy released when an atom accepts another electron. The more negative the energy, the more it wanted the electron. So when we think of these atoms, like fluorine and chlorine and bromine and iodine, these are atoms that want another electron. And when they do get that extra electron, it actually causes them to release some energy because they become more stable. And stability relates to a lower energy level with atoms. So we can see that for some of these, it's down here at 0. They don't want any more electrons. They don't need any more electrons. But we can see this trend that as we go across the row, electron affinity increases. And by increasing, we mean the amount of energy being released becomes greater. It gets more negative. So if we wanted to draw the trend here, we're going to say that it becomes more negative as we move across, and that's because these are the atoms that want to accept those electrons, and when they do, they're going to release a lot of energy. So it becomes more negative as you move across, and it becomes less negative as you go down. So there's electron affinity, a little different than electronegativity. And that's it. So make sure that you understand those trends and why they are, especially ionization energy is a big one, and electron affinity, which we'll also talk about electronegativity and how they relate. But understanding the trends and why you see those trends is a really important part of this podcast.